All right, so today we're going to look at different things. So a table, contextual information, the graph of the function, or the graph of the rate of change, and decide what type of model best fits the data. So we're going to have 6 different models to choose from. All right, so these are the 6 different types that we're going to choose from today. We will learn other types of models, so we'll learn exponential and logarithmic and sinusoidal, but that's going to be later. So today, these are going to be our 6 options. And so we're going to fill in, some of these are going to have a whole bunch of words, some of them are going to have less. Constant is definitely going to have less. So when you think of a constant function, what does it look like? Oh, horizontal line, yeah. So a constant function is horizontal. And it is unchanging. And there honestly are not a whole lot of real life situations that are modeled by a constant function, because almost everything I can think of changes. So it's pretty rare that that's going to be the answer choice, but it is possible. All right, linear. So linear, one of the first things we learned were about first, second, and third differences. Which differences are in the output values are constant for linear? First. So we're gonna write out the whole thing on this one, and then on the others we'll just kind of do dot dot dot, because we have a lot to write today. So on linear, the first difference is, and what are the differences of? Output values. And we're going to say are roughly constant. Because when we're looking at like real world data, there is no perfect linear function in real life. So the ones we were doing so far, they haven't really represented anything, so we can make them perfect. These are going to be roughly constant. Over, what are they over? Consecutive, equal length, input value intervals. So that's what you're going to see if it's in the table. You're going to look at the differences. Another thing we talked about whenever we were learning this, like we learned like 3 different ways to do it. So these are also going to have roughly constant rates of change. All right, so on this one and on quadratic, we're going to do a graph of a function. That would be linear. And we're going to do a graph of rates of change. That would represent a linear function. All right, bless you. So I know we all know what a linear graph looks like. So we're just going to do a scatter plot that kind of all the points line up roughly linear. Now, it doesn't have to be perfect line. So sometimes that's what you're given. You're given the graph of the function, and you can just look at it and tell, like automatically that looks like a line. But sometimes you're given the graph of the rates of change. And it will tell you, it'll tell you in the context of the problem, it will also tell you on the graph that it's the graph of the change, not the actual graph of the function. But you have to pay attention, and it'll sneak up on you. Like you'll be doing a whole bunch of them one way, and then they'll just throw one in there. But if the function is linear, the rates of change are going to be constant. All right, and then for quadratic. For quadratic, the second difference is outputs are roughly constant. Over, and we're just going to do dot, dot, dot. If you want to write it all out again, you can, but I'm pretty confident you got that down. All right, so on the linear function, we said that they're roughly constant rates of change. Do you guys remember what the rates of change are for a quadratic function? Nice, linear. So we're going to say roughly linear rates of change. All right, so I'm going to do a little graph of a quadratic function and then a graph of the rates of change of a quadratic function. All right, and I feel confident that everybody kind of knows what a parabola looks like for a quadratic function. Now, sometimes you'll just have half of a parabola, and you kind of go with that, but I think you guys are good there. But when you're paying attention to what the graph is of, if it's a change graph and it's linear, that means that the original function was quadratic. Okay, I have a couple more things to fill in this box. All right, sometimes you're given just words that describe the scenario or contextual situation, and if it has to do with geometry, if the context involves area, it's going to be, the model would be quadratic. So for geometric contexts, involve area. So sometimes you just kind of have to read what's happening in the problem. If it involves area, go ahead and say that it's a quadratic model. And one more thing about quadratics is a quadratic function only has a max or a min. So if your data just changes direction multiple times, it cannot be quadratic. It has to be a different type of function. All right, let's talk about cubic. What differences are constant for cubic? Third differences? right, if area kind of translates to quadratic, what do you think translates to cubic? Volume, good. So geometric contexts involve volume. Right, and cubic functions can have two turning points. Something like that, where you have a max and you have a min. Right, and then the main thing I need you guys to know about rational, we'll talk more about tomorrow also, is that rational functions have inversely proportional relationships, and I'll tell you what that means. That means as one variable increases, the other decreases. So for example, something that would have an inverse relationship would be like how much time you spend golfing and your score golfing. So as you spend more and more time practicing, your score that you get when you golf should go lower and lower and lower. That's an inversely proportional relationship. All right, and then the last type is piecewise, which is what we talked about yesterday. And mainly for piecewise, there's going to be more than one pattern. So what that would look like on a graph would be something like this. Like it's constant, and then all of a sudden changes to linear. That's more than one pattern. All right, so the rest of this should go pretty quick. There's a bunch of words to read, but there's not much writing to do. All right, so on example 1, or on all these examples, we're going to determine the function type that best models the scenario. On number 1, a bottle company is researching how the dimensions of a bottle affect its weight. The water bottles will be 2.5 times as tall as they are wide. If water weighs 0.03615 pounds per cubic inch, what type of function could be used to predict the weight of a water bottle with a diameter of X inches? So if we're talking about how much you basically can fit in a bottle, what geometric context are we talking about here? Volume. So if it's a volume, what type of model would it be? Nice job. That's all you have to write. If you need a little reminder of why we chose that, we chose it because this situation is talking about volume. All right, so for number 2, an organization sends out an annual Christmas newsletter in the mail. Last year, it took 7 volunteers 4 hours to stuff, address, and stamp all the envelopes. What type of function can be used to model the time it takes to complete this year's mailing if there are X volunteers? This one's a little more difficult, I think, than the last one. Yes, this one is rational because as the number of volunteers increases, the time it takes to stuff the envelopes decreases. All right, so for number 3, the graph shows the difference between average female and male life expectancy from 1940 through 2014. What function model might you use to describe the relationship? What do you guys think? What does that look like to you? It's a quadratic to me. You could make a case for piecewise because it kind of goes flat. But part of that going flat is where it says United States. So I'm going to go with quadratic on this one. Right. And then for number 4, a restaurant owner collected information about how many customers are at his restaurant T hours after it opens at 11 a.m. What type of function would best model this data? All right, what do you guys think we need to do?
Like a rate of change.
We could do rate of change, or we could just do differences. So if you notice that these all just increased by 1, they're consecutive equal length input values, then we can just do the differences where we'll just find how much this has changed. All right, those are not roughly constant, so this is not linear. And so then we find the second differences. Those are also not roughly constant, so it's not quadratic. So let's try the third differences. What do you guys think? Are those roughly constant? That's roughly constant. That's pretty good for a real life situation. These probably are just made up numbers anyway, but we're going to say that this one is cubic. And then for number 5, the graph shows how the average annual number of working hours has changed in the United States over time. What function might you use to describe this relationship? This is definitely piecewise. And I would say that it's linear, and then linear, and then linear, and then constant. So I'm going to describe it. You don't necessarily have to. So I'd say there's at least 4 pieces to this function. All right, and then number 6. Market research has shown that increasing the monthly subscription cost of a coffee sip club by 50 cents decreases the number of subscribers by 12,000. The scatter plot above shows the change in subscribers for each monthly subscription price. A function model R is to be constructed for the amount of revenue earned by the company at monthly subscription price of P dollars. Which type of model would best represent the revenue? Is this a graph of the revenue? No. This is a graph in the change of subscribers, which also would translate to the change in revenue because less people, less revenue. So if the change is linear, then what should the function be? Yes. R is quadratic. And the reason is the change is linear. All right, what questions do you guys have?
Is there a rate of change?
There is.
Quadratic or cubic?
The cubic does have a quadratic rate of change. That is not something you have to know for pre-calculus, but that is what happens. It does have a quadratic rate of change. All right, any other questions? Okay, now on your worksheet, when it's a graph of the change, I did kind of like bold it out in the words. That won't happen on the AP test, so just be careful to pay attention to stuff like that.